Hey everyone, welcome back, and let's write some more Leetcode today. So today let's solve the problem prime subtraction operation. This is an interesting problem, a decent amount of math, but also some conceptual challenges with this problem. I'll be showing two solutions. One is more of a brute force solution, but it actually does pass on Leetcode, and I would say that honestly a brute force solution, given that this is a medium problem, isn't the worst thing. It very well may pass you in the interview. I will also show you a second, more optimized solution, which maybe for a medium problem, you might need a hint to come up with the solution. So we're given an input array. All of the integers are going to be positive. That's guaranteed. We want to transform this array. Well, we don't actually want to transform it, but we want to know if we can transform it such that it will be sorted in strictly increasing order, not non-decreasing order where like adjacent elements could possibly be equal. That's not allowed. They have to be in increasing order. So is it possible to do that? Well, the rules of the game are this. We can pick any element and we are allowed only to subtract from that element, and we're only allowed to subtract prime numbers. So knowing that, how can we solve this problem? I'll kind of walk you through my line of thinking. It was this. If we pick an element, first of all, we can pick in any order that we want, but it probably makes sense to go left to right. So that way we can kind of validate, okay, this portion was sorted, this portion is sorted, now this portion is sorted, etc., etc. So we could start from the beginning of the array, trying like a brute force approach. We look at 4, it's already sorted, right? Like the next element is greater than 4, the previous element doesn't exist, so we're good. So okay, move to the next position. 9, it's greater than 4, but it's not less than 6, so we should subtract from here. There's a prime number, I'll just randomly pick one, 7. We could subtract 7 from 9, then it would become 2. Okay, that's technically less than this, but it's not less than the previous, or it's not greater than the previous value. So now you might think, okay, this seems like a backtracking problem, right? So I have to brute force this. I have to make a decision tree. I might have to go back. But no, that's actually not the case. We can, instead of going back to 2 and seeing, okay, well, is there a prime number I can subtract from 4? Yes, there is. We can subtract 3 from 4, and then it'll be 1. And then this portion of the array is sorted. Instead of having to backtrack and do that, why don't we just be greedy? We just want the array to be sorted. We don't necessarily know what's coming up ahead. We really don't. I mean, there could be some really small values here. For example, like this could have been a 3. So what kind of greedy approach should we take? Knowing that we can't predict the future, we should try to, every time we look at an element, not only should we try to make it such that it's sorted, like it's less than the next element and greater than the previous, but we should also try to minimize each element. How are we going to minimize each element? Well, we can only subtract prime numbers, so thus we will choose the largest prime that we can subtract from each element as we go. This way, we don't need to do any backtracking or anything like that. By the way, one thing I didn't mention earlier is that yes, we're allowed to subtract primes from any of these given numbers, but we also want every value to remain positive. So we can subtract like the largest possible prime, but if a number itself is prime, like for example, if we had 7, we are not allowed to subtract 7. The largest prime we would be able to subtract is 7 minus 1, which is not a prime number. Just keep that in mind. So knowing all that, this is how we can solve the problem. Okay, for the first number, 4, what's the largest prime we could subtract from 4? Well, we can brute force just getting every number that's less than 4. So 1, 2, 3, these are all the numbers less than 4. In other words, this is the upper bound of all the numbers less than 4. And so among all of these, we want to figure out which one of them is the largest prime. So we can kind of go through these in reverse order. Check, is this a prime? If it is, then we can stop. We found the largest prime. If it's not the largest prime, we will go left and try to see if there are any primes here. Now, in this case, 3 does happen to be prime. So 3 is the number that we would subtract from 4. Now, how would you determine that a number is prime? Well, the brute force way to do it would be like this. A number n is considered prime as long as there doesn't exist a factor or denominator that can divide it such that like the remainder will be 0. So does there exist an f? If it does, then this is not prime. And if there does not exist an f, then this guy is prime. How do we check that? Like this. Just get every factor from 2 all the way up until this number. But actually, if you want, you can stop early going all the way up until the square root of that number, because we don't need to check any factors beyond the square root. And if you want the intuition of why that is, consider something like 49, where the square root of it is 7. So we would only need to check up until 7, because anything else, like for example, even if there was a factor over here, it must be multiplied by a number that's less than the square root. And if this is a factor, then we would have already found the factor here. And that's why we can stop at 7. So knowing all of that, now we can solve the problem. Assuming we have a way to find the largest prime, we can do this. Take 3, now subtract it from 4. We're good. We'll have 1 here. And now we'll move to the next position. We want to know what the previous element was, because we do want to make sure that this is greater than the previous element. So now from here, we want to do the same thing. Just remove the largest possible prime. And in this case, that happens to be 7. So if we subtract 7 from 9, we will get 2. And that is greater than the previous element. But it could have been possible that maybe we got a number that was less than the previous element. An easy way to avoid that is, rather than checking all prime numbers from like 1 through 8, remember we skipped the 9 because we don't want to set this to 0. Rather than checking if these are prime numbers, we know that if 8 happened to be a prime number, we would not want to subtract it from 9, because if we did, we would end up with 1 here. We want the array to be in increasing order. This is not the case. So what we actually do is we take the current element, 9, subtract it from the previous element, 9 minus 1. That gives us 8. So now I'm going to check all numbers less than 8, so 1 through 7, and check if any of those are prime. So you can kind of think of it as like this being the upper bound of numbers that we need to check. And the upper bound is not inclusive. So basically we check everything less than that. And I know I said 1 through 7, but I actually meant 2 through 7, because we already know that 1 by definition is not a prime number. Anyways, now let's code it up. I'll just leave these comments in case they're helpful, but we can get started now. I'm going to define a helper function is prime so that we can determine if a given number is prime, because remember, we are going to kind of brute force this. So given n, is it prime? For now, I'm just going to assume that it works, and we're going to use it to solve the rest of the problem. And then we'll come back and fill it in. I want to go for n in nums, every number. I want to calculate that upper bound I was talking about. So I want to take n and subtract from it the previous numbers. So I'm just going to have a variable for the previous number. Initially, we can just set it to a neutral value like 0. We already know that 0 is less than every number in the input, because every number is going to be positive. And we also know that since it's a neutral value like 0, it's not actually going to change the value n. And this is the upper bound. But remember, the upper bound is not inclusive. So this is technically not the largest number that we could subtract from n. This is non-inclusive. I'll just make a comment for that, non-inclusive. The largest prime we could subtract is technically this minus 1. So keep that in mind, but when it comes to Python, it won't be a problem. You'll see why. So I want to figure out what is the largest prime. Again, I'm just going to initialize it to a neutral value like 0, basically saying we have not found a prime number yet. So now I'm going to check every number. For I, is I a prime number? I'm going to go from 2 up until the upper bound. In Python, this second parameter is not inclusive. So this loop is going to check everything from 2 up until upper bound minus 1. We skip 1 because 1 is not prime. And also, for this, we could go from left to right, but it would probably be better to go from right to left because we're just trying to find the largest one. If we find one, we can just break out of this loop. So I'm actually going to take this and reverse it. And then in here, I'm going to call is prime on I. If it is prime, I'm going to set largest prime equal to that number. And then I'm going to immediately break out of it. As soon as we find a single prime number, we break because we're checking from largest to smallest. Now, after that is said and done, this is the largest prime we were able to make. We should check that n minus the largest prime, because remember, that's the whole point of finding the largest prime, to subtract it from n, if this is greater than the previous number. Well, if it's greater, that's good. But if it's not greater, if it's less than it or equal to the previous number, that's bad. We return false because that means it's impossible to make the array in ascending order. And so then down here, if we didn't execute this return statement, we can then actually update the previous number, set it to be n minus the largest p, so that it can be updated for the next iteration. And this is pretty much it. If we never return false here, then we will assume that we did indeed put it into sorted ascending order. And the only thing left for us to do is to fill in this little helper. Normally with an isPrime function, you'd want to add like an if statement to check if the number is less than 2, or even if it's negative, then you would want to return false. We say that that would not be a prime number. But the reason we actually don't need to add this time is because we already start at 2 anyway. We'll never go below 2 when we pass like I in as a parameter. So we don't need to do that. So I'll just not put it there. Then we want to check every factor of n from 2 up until the square root of it. So for f in range from 2 up until the square root of n, which could be a decimal, so we want to round it, and this will round it down. Converting it into an integer will round it down if it's a decimal. And since this is non-inclusive in Python, we will just add like a +1 here, because we do want to try the square root. We know that that's a factor of n, and we want to determine if that's a prime number. So we can determine if n is a prime number if it can be modded by the factor that we are choosing. And if that remainder equals 0, then n has a factor of f, so it's not a prime number. We return false. Otherwise, if we never find a factor, we can return true. That means it is a prime number. So this is the entire code. Let's give it a run. And as you can see, it works, and it's actually relatively efficient. If we analyze the time complexity, we can clearly see this loop is going to iterate n times, so big O of n, and the inner loop here is going to iterate this many times the upper bound. In the worst case, what could the upper bound be? Well, proportional to n, an element inside of the array. So what's the max number inside of that array? That's kind of what this is proportional to. So we'll call that m. So n times m. Now inside of this loop as well, we have a function call. And unfortunately, that function call actually has a loop inside of it as well. But this one isn't so bad. What we're passing into it is a number. In the worst case, again, it could be the maximum number. But when we iterate, we're not iterating m times, we're iterating the square root of that number. So here we'll do times square root of m. So this is the overall time complexity. So it depends a lot on the max number. Square root usually isn't super inefficient. This might be inefficient though. So in terms of optimizing this solution, I'm actually going to show it to you just in this code because I honestly think it's easier to explain in terms of code. Most of this code is pretty straightforward. I think one of the big bottlenecks we can see here is we're calling isPrime on a bunch of numbers. For example, this sequence from 2 up until upper bound. Maybe one of the times we do that, it'll be something like this, from 2 all the way to 7. And maybe the next time we do it, it'll be 2 all the way to 4. And maybe the next time, 2 all the way to 9. For each number in this range, we're going to determine if it's prime. We're going to ask, is 2 a prime number? Is 3 a prime number? Is 4 a prime number? And clearly, it's repeated work. We're doing it multiple times. So why don't we just pre-compute those prime numbers, and then we won't have to make this function call? Well, how do you pre-compute it? How do you know how many numbers to pre-compute in the first place? Well, without using like the constraints of this problem, which is kind of a shortcut, we can clearly see that whichever like end value among all of these is going to be maximal is the one that we would choose. This is like the upper bound, and what could it possibly be as the max value? Well, n is a number in the nums array, so the max value in the nums array minus 0, because that's like the smallest that this could be. So we only need to compute prime numbers up until then, up until the upper bound. And really, we could probably do upper bound minus 1. So that's exactly what I'm going to do. I'm going to do some pre-work up above here. Rather than calling this here, I'm going to create an array, which I'm going to call primes. We already know that 0 and 1 are not prime, so I'm going to have an array and fill the first 2 values with false. What this array represents, primes of I, is going to be true if I is equal to a prime number. So we're going to go through every number for I in range 2 up until the max in the nums array. This is technically not going to include the max number because we know that in reality, the upper bound is going to be the max number minus 1. Like that's the highest it could actually be. So that's why it's done this way. You could do a +1 here. It's not going to hurt. But anyways, we want to know, is this number prime? Let's do the function call. Let's check if is prime I. And if it is, let's set primes of I to be true. And we actually have to append in this case. So I will do that. Append this to true. Otherwise, append it to false. And this works. We did the pre-computation. So now we're going to make an intelligent decision down here. Instead of making a function call, which we know is square root of n, we're going to do a array lookup, which is constant time. So rather than is this prime, let's use the array primes at index I. And then the rest of the code stays the exact same. So I'll just quickly run this to you to prove that it works. And you can see that it does. I believe the runtime actually might be less than the other one. But anyways, in terms of big O runtime, this is more efficient. I'll quickly analyze it. Analyzing this part here, we can see we're still looping n times in the outer loop. So we're going to get n. And the inner loop, we still have that inner loop, which is going to iterate m times. So n times m. And plus for the work that we did up above. Here we're iterating m times the max number, and then inside of there we're calling is prime. We know that's square root of m, so this part is m times square root of m. So it is an improvement. You can see that the largest term up above is going to be larger than either of the terms down here, given the fact that like all of these are going to be integers and not like decimals that are less than 1. Now you might think you're done, but actually there is a way to do it even better. We can get rid of this loop in here as well. And that's actually going to require being a tiny bit clever. We can actually make this array a little bit better because what we really want to know is with this upper bound, what is the largest possible prime? Well, in reality, we're doing upper bound -1 because we know in Python, these loops, this is not inclusive. But anyways, what I'm trying to say is I want to change the definition of this array up above. I want primes of I to be equal to the largest prime that is less than or equal to I. This represents the largest prime less than or equal to I. Because if I had an array like this, if I had one, this is what I could do. I could just say down here, don't give me a loop. I don't want that. Largest P, I already know what that is. I pre-computed it. For this particular upper bound, it'll be this, upper bound -1. Because again, that upper bound was non-inclusive. That's how we defined it originally. So now the only thing is, how do we build an array that satisfies this definition? Well, let's say I was trying to determine is a 7 prime? Like I is equal to 7. So let's just do that. I equals 7 is 7 prime. Because if 7 is prime, then obviously that's the largest prime that's less than or equal to I. Like that's the largest it could possibly be. So that's what we should check first. And if it's not, well then the largest prime less than or equal to 7 is going to be the same as the largest prime less than or equal to 6. Because remember, this isn't prime factorization. We're not checking if that prime number is a factor of this. We're just checking what's the largest prime number that is less than or equal to this. And if 7 is not prime, then get the largest prime less than or equal to 6. So this is how we would compute it. For the first two positions, I'm going to put 0 and 0 because we know that 0 and 1 technically don't have like prime numbers that are less than them. But then we will loop, similar to how I've done it below actually, from 2 up until the max number, and we'll check if that number is prime, then append to this array the number itself. It's the largest number that's prime, less than or equal to that. Otherwise, we will append to it the previous prime at I -1. Now, the base case is really 2 because 2 is a prime number, so we're going to have 2 appended here. And then we'll just kind of keep going. We'll say, okay, now give me 3. Okay, now is 4 a prime number? Nope. So the largest number that's less than or equal to 4, that's prime, is actually the previous number, 3. Then we'll check, is 5 a prime number? Yes, it is. 5's a prime number. 6 is not, so we give it a 5. Is 7 a prime number? Yep. So that's just kind of the dry run. But this is pretty much it. That's the whole code. And this further time complexity, you can see that the pre-work we're doing up above is still technically m times the square root of m, but the loop down here is just n. So for the new time complexity we have is this, getting rid of that and this. This is the final time complexity of the solution I'm showing you right now. And it's definitely an improvement over the previous, first one that we had. Let's give this a run. You can see that it works. I guess the runtime on Leetcode was worse than the others, but I can confidently say that at least big O runtime, this is more efficient. If you found this video helpful, definitely consider checking out Leetcode.io. It's got some really incredible free resources. You can see that it definitely took a lot of time to create this stuff, and I honestly think it'll be valuable for you. If you haven't heard of it, I know most people have already heard of it, but still worth mentioning. Thanks for watching, and I'll see you soon.